While teaching on the origin of the 90 East Ridge, I was asked, why is it that the ridge is located right under the Himalayas and not somewhere else? Why didn't it rip over to the side along the mid-oceanic ridge near Africa, or out in the fractured western Pacific somewhere else? It was a good question that made me realize the need to add more detail to visually explain and answer this question. The main driving force was due to the centrifugal force as the Earth's bulge tipped away from the equator. The way in which the bulge tipped away from the equator determined where the rip would occur. As we'll see, where it tipped the most, the material was correspondingly stretched more before reaching equilibrium. The greatest tipping from the equator occurred in line with the location on the surface where the mass was the most concentrated, the Himalayas. These are the answers, but they may not be so easy to see and understand, so let's step through the situation in detail. Remember that a roll is induced due to where the mass concentration is on the surface of the spinning object. Remember the roll occurs because everything is spinning, and the mass concentration, m, has greater centrifugal force acting on it than the adjacent material next to it. Since the Himalayan mountains are the tallest, they were the furthest radially from Earth's center, so this force acted at a greater distance. The mass concentration therefore has the most leverage and determines the direction of roll. Wherever the mass concentration is, a line may be drawn from the mass to the axis of spin. 90 degrees to that line, another line may be drawn along the surface down to the spinning object's equator. For situations where the surface mass is small compared to the spinning object's mass, connecting these 2 points through the axis of spin gives the location of the axis about which the surface will roll as the object continues to spin about the spin axis. As discussed in the hydroplate theory overview presentation, where you are on the surface will depend on how much roll movement is experienced. Surfaces in line with the mass concentration will roll greater distances than surfaces adjacent to the concentration. Notice that this roll axis spins with the object's spin axis. As the object rolls due to the mass concentration, locations on the surface change relative to the spin axis, which does not change its orientation. If the mass concentration were to be moved to a different location on the surface, then the surface will roll along a completely different roll axis. This situation is important to understand now as we remember that due to the Earth's spin, centrifugal force causes the equator to bulge. Remember from the overview series the analogy where we imagined that a red cord was wrapped around the surface at an angle through the roll axis. As Earth rolled about this axis, the bulge tipped away from the axis of spin as shown. As can be seen, the bulge tips a great deal more the further away it was from the roll axis. It is at these points that the centrifugal force on the bulge was the greatest. Remember that the greatest mass concentration on the surface was the Himalayas on the largest continent, Asia. Following the same methodology, we can determine the roll axis location. Notice that at the roll axis, the bulge does not tip away from the new equator at all. However, 90 degrees from this, the bulge tips away from the equator the most. Notice that by definition, the location of the greatest tipping of the bulge aligns with the mass concentration, the Himalayas. Now let's look at why stress would be the greatest at this location. Directly under the Himalayas was the location where the bulge tipped away most, so centrifugal force in this area was naturally the greatest. Locations adjacent to this extreme tipped away from the equator less and less, so the centrifugal force in these areas was also less. These forces acted at these locations to deform the mantle along the new equator where we've imagined our red cord is at. The blue line represents the distance the mantle would deform to reach equilibrium and reform a new bulge at the new equator. Now notice that since the bulge did not tip away at the roll axis, there is no centrifugal force, no stress, and therefore no displacement of material. However, as we travel along the surface of the equator away from the roll axis, the displacement to equilibrium distance increases to a maximum, again directly under the Himalayan mass concentration. Therefore, we expect that the location of greatest stress and displacement in the mantle will always be in an area directly south of the Himalayas, or its antipode on the surface on the opposite side of Earth, since it too had tipped an equal distance away from the equator. If everything was exactly equal in every way, then we would expect that 2 rips would open up and we should see a second 90 West ridge directly opposite of the 90 East ridge. So why didn't a second ridge form here on the opposite side of Earth? In nature, perfect symmetry is rare. As you can see, conditions for the mantle on the opposite side were much different, with the North American plate resting above. As explained in the hydroplate theory overview series, the mantle in the western hemisphere was not as heavily fractured as in the Indian Ocean and Western Pacific. The subsidence of the Western Pacific and Indian Oceans greatly fractured the mantle, so these areas were structurally much weaker than their antipodes in the Western Hemisphere. It is for these reasons that the hydroplate theory expects this uniquely straight formation should be located, as it is, directly under the Himalayas.